Welcome to G Fun Facts Online. Today we're talking about a breakthrough that sounds like science fiction, taking the material at the heart of our computers and making it a perfect, resistance-free conductor of electricity. For decades, two titans of technology have lived in separate worlds. In one corner, you have semiconductors, the silicon and germanium that form the bedrock of every computer, phone, and digital device. They are masters of control, meticulously directing the flow of electrons to process information. In the other corner, you have superconductors, materials that offer a utopian promise, electricity flowing with absolutely zero resistance, zero energy loss. The dream of uniting them, of creating a single material that is both a controllable semiconductor and a perfect superconductor, has been one of the holy grails of materials science. That dream just took a giant leap into reality. An international team of scientists has successfully coaxed germanium, a workhorse of the electronics industry, into becoming a superconductor. This isn't just a small step. It's the creation of a new class of material that could unlock scalable quantum computers and ultra-efficient electronics by merging the quantum world with the classical world, all while using the manufacturing tools we already have. This is the story of the germanium revolution. To understand why this is such a big deal, we need to quickly look at these two separate worlds. Let's start with superconductivity. The story begins in 1911 with a Dutch physicist named Heineke Kamerlingh Onnes. He had just figured out how to liquefy helium, creating a refrigerant that could cool things to just a few degrees above absolute zero. While testing the electrical resistance of solid mercury, he saw something incredible. As he cooled it to 4.2 Kelvin, about -269 degrees Celsius, its electrical resistance didn't just get low, it vanished completely. An electric current, once started, could flow forever without losing any energy. It was a perfect, frictionless highway for electrons. This defied everything known about electricity. Normally, electrons bump into atoms in a wire, creating friction and wasting energy as heat. That's why your phone charger gets warm. Superconductors had no such problem. Then in 1933, another bizarre property was discovered: the Meissner effect. When a material becomes superconducting, it actively expels all magnetic fields from its interior. This is what allows a magnet to levitate above a superconductor, a classic image of physics in action. It proved superconductivity wasn't just perfect conduction, it was a whole new phase of matter. But for nearly 50 years, no one knew how it worked. The answer came in 1957 with the BCS theory, named after its creators Bardeen, Cooper, and Schrieffer. The theory is complex, but the core idea is beautiful. At extremely low temperatures, electrons, which normally repel each other, can form pairs called Cooper pairs. This pairing is indirect. An electron moves through the crystal lattice of the material, and its negative charge pulls the positive atomic nuclei slightly inward. This creates a temporary ripple of positive charge, a wake, that a second electron is attracted to. This attraction binds them together. These Cooper pairs behave differently from single electrons. They can all condense into a single low-energy quantum state. In this synchronized state, they move as one. There isn't enough energy in the system to scatter just one pair. You'd have to disrupt the entire collective. This collective quantum lockstep is what gives rise to zero resistance. Now, let's turn to the other world. Semiconductors. Materials like silicon and germanium aren't great conductors or great insulators. They're somewhere in between, which is what makes them so powerful. Their conductivity can be precisely controlled through a process called doping. Doping means adding a tiny amount of impurities. If you add an element with an extra electron, like arsenic, into a germanium crystal, that extra electron is free to move around and carry current. This is called an N-type semiconductor. If you add an element with one less electron, like gallium, it creates a hole, a missing electron. This hole can also move around like a positive charge, creating a p-type semiconductor. By putting n-type and p-type regions together, you can build transistors, the microscopic switches that are the basis of all modern computing. And here is the fundamental conflict that has kept these two worlds apart for a century. A semiconductor's function relies on controlled disorder, the intentional introduction of dopant atoms, but conventional superconductivity relies on pristine order. The formation of Cooper pairs needs a clean, stable crystal lattice to mediate the pairing. For years, any attempt to make silicon or germanium superconducting failed. To get enough charge carriers to support superconductivity, you had to hyperdope them. Add so many impurity atoms that you completely wrecked the delicate crystal structure, killing any chance of the quantum coherence needed for superconductivity. The two most important materials in electronics were fundamentally incompatible. This brings us to germanium, the comeback kid of the semiconductor world. While silicon dominates the industry today, the very first transistor was actually made from germanium. Germanium has some key advantages over silicon. Charge carriers move through it much faster, which means you can build faster switching transistors for high-frequency applications like 5G communications. In recent years, germanium has experienced a renaissance in the field of quantum computing. It turns out to be an excellent material for hosting spin qubits. A qubit is the quantum version of a bit. It can be a 0, a 1, or both at the same time. One way to make a qubit is to use the spin of a single electron or hole, trapped in a tiny structure called a quantum dot. Germanium is great for this because it allows for fast, electrical control of these qubits. So you have this material, germanium, that's already compatible with the chip industry and is a rising star in quantum technology. It was the perfect candidate for the audacious goal of bridging the semiconductor-superconductor divide. If you could make it superconducting, you'd be upgrading a material that's already a cornerstone of advanced tech. The international team behind the breakthrough knew they had to solve the doping paradox, how to cram a huge number of dopant atoms into germanium without destroying its crystal. Their solution was a sophisticated fabrication technique called Molecular Beam Epitaxy, or MBE. You can think of MBE as atomic-scale 3D printing. Inside an ultra-high vacuum chamber, you fire beams of atoms, in this case, germanium and the dopant, gallium, at a substrate. The process is so slow and controlled that the atoms arrange themselves one layer at a time, forming a near-perfect crystal. Using MBE, the researchers were able to force gallium atoms into the germanium crystal structure at concentrations far beyond what was thought to be stable. Advanced X-ray analysis confirmed that the gallium atoms were properly substituting germanium atoms within the lattice. They had successfully created hyperdoped germanium films with a massive density of charge-carrying holes, all while preserving the crucial crystalline order. The result was spectacular. When they cooled the film down to 3.5 Kelvin, its electrical resistance dropped to 0. They had created Super-GA, a material that was still fundamentally a semiconductor, but could now also act as a perfect superconductor. To prove this wasn't just a one-off laboratory trick, they took it a step further. Using standard, industry-compatible manufacturing processes, they fabricated millions of microscopic Josephson junctions across a wafer. A Josephson junction is the fundamental building block of superconducting electronics and a leading type of qubit. By showing they could make dense arrays of these, they proved their discovery was a viable platform for building complex, integrated superconducting circuits. So what does this new super germanium actually allow us to do? The implications are massive and can be grouped into three main areas. First, and perhaps most excitingly, is the impact on quantum computing. One of the biggest challenges in building a large-scale quantum computer is the interconnect problem. The most powerful qubits, superconducting qubits, are incredibly fragile and have to operate at near absolute zero. But the classical electronics needed to control and read them are standard silicon chips, that work at room temperature. This creates a wiring nightmare. You have to run thousands of individual wires from the warm control chips down into the cryogenic refrigerator. This complex wiring adds heat and electrical noise, which can destroy the delicate quantum states of the qubits. It's a huge bottleneck that limits how many qubits you can scale up to. Superconducting germanium offers a stunningly elegant solution. Because the material is compatible with standard chip manufacturing, it opens the door to creating a monolithic quantum processor. On a single piece of germanium, you could build the quantum components, like qubits and their wiring, out of the new hyperdoped superconducting germanium, right alongside the classical control circuits made from standard, lightly doped germanium. Everything sits on the same chip at the same cryogenic temperature. This eliminates the wiring nightmare, reduces noise, and makes the whole architecture vastly more scalable and integrated. It's a game changer for building a quantum computer with thousands or even millions of qubits. The second major implication is the connection to manufacturing. In the world of materials science, the phrase "compatible with existing foundry workflows" is pure gold. The global semiconductor industry has invested trillions of dollars perfecting the manufacturing of silicon and germanium chips on 300mm wafers. The ability to create superconducting components using the exact same tools and processes is a monumental advantage. Before this, integrating superconductors into electronics meant using exotic materials and specialized, expensive fabrication methods that were impossible to scale. This discovery provides a roadmap for the mass production of superconducting circuits in the very same factories that make our current computer chips. This could lead to a new class of cryo-CMOS electronics. The massive data centers that power AI and the internet consume enormous amounts of electricity, much of it wasted as heat from resistance in the wiring. Building chips with superconducting interconnects could dramatically reduce that power consumption, potentially leading to a 100-fold increase in energy efficiency. Imagine supercomputers that are not only 10 to 100 times faster, but also vastly more sustainable. The third area of impact is a whole new frontier for sensors and electronics. Superconducting materials are incredibly sensitive to magnetic fields. This makes them perfect for advanced sensors. For example, devices called SKUYIDs, or superconducting quantum interference devices, are the most sensitive magnetometers we can build. They're used in medical imaging to map brain activity. Integrating these ultra-sensitive sensors directly onto a semiconductor chip, with its own processing logic, could lead to cheaper, smaller, and higher resolution medical devices or brain-computer interfaces. The same goes for astrophysics, where highly sensitive detectors are needed to pick up faint signals from distant galaxies. Superconducting germanium detectors could operate with lower noise and higher efficiency, pushing the boundaries of what we can observe in the universe. Of course, the germanium revolution is just beginning. The critical temperature of 3.5 Kelvin is still very cold, requiring expensive liquid helium. While that's already standard for quantum computers, a major goal for future research will be to find ways to raise that temperature, perhaps by trying different dopants, to make the technology accessible for a wider range of applications. But even as it stands, this achievement represents the crumbling of a wall that has long separated two of technology's most important pillars. For decades, we have built our digital world on the controlled imperfection of semiconductors, while dreaming of the perfect efficiency of superconductors. Now, a single material, germanium, promises to deliver both. This discovery is a blueprint for the future. It paves the way for scalable quantum computers, built with the tools we already have. It offers a path to a new generation of sustainable supercomputers. It's a new toolbox for engineers to build devices we've only theorized about. We are at the dawn of an era where the strange and powerful rules of the quantum world can be seamlessly integrated with the classical electronics that run our lives. The age of the superconducting semiconductor has begun. Thanks for listening to Fun Facts Online.